Okay, now let's look at the temperature dependence on rate. And to do this, we're going to look at the Arrhenius equation. Now, note for a normal rate law, rate equals K times concentration of reactant to some power X. Temperature doesn't affect concentrations of reactants unless reaction is happening. Just the concentration of reactant isn't affected by temperature, which means the temperature must affect the rate constant itself. And so the Arrhenius equation here looks at how temperature does affect the rate constant, where K is our rate constant. A is the pre-exponential factor, which has to do with a number of things, including how the two molecules can collide and get the reaction to occur. For example, down here, for this reaction here, if you had our potassium that's going to react with the CH3I, note that the potassium and the iodide have to be on the same side. This potassium has to come in there and smack into this iodide to get the reaction to occur. If the potassium smacked into the CH3, in this orientation, it will not occur. So this molecule has to be oriented correctly for that potassium to smack into the iodide. Now, all of these collisions are completely random. All the molecules are in random orientations, so sometimes it smacks in this way and the reaction happens. Sometimes they hit this way and the reaction doesn't happen. Note, if you had a different molecule, instead of a CH3, you had a big organic group here that's really blocking. There's really only one way the potassium can come in, only from this direction here. So this reaction would be slower than this one, because in this reaction the potassium can only come in from one direction, and realize they're moving randomly. Whereas in this reaction the potassium can come in this way, it could come down this way, it could come up from here. Multiple collision dynamics, multiple collision orientations will allow this reaction to occur. Really only one will allow this reaction to occur. So that's our pre-exponential factor. And it's called the pre-exponential factor because it comes before the exponent E. But this exponent E is to the negative EA, or activation energy, divided by RT. R is the gas constant, 8.314, and T is the temperature in Kelvin. Now that equation is nice, but let's do a little math with that equation. Turns out you can take the natural log of both sides of this equation, and when you do that, you get natural log of K equals negative EA over RT plus the natural log of A. And note this is in the form of Y equals mx plus b, where natural log of K is Y, the slope of the line is negative EA over R, the x-axis is 1 over T times natural log of A. So you can run some experiments, calculate the equilibrium constant at various temperatures, graph the natural log of the rate constant, calculate various rate constants at various temperatures, plot the natural log of the rate constant on the y-axis, 1 over that temperature on the x-axis, and this straight line will give you the activation energy and will give you the pre-exponential factor. What you can also do is you can compare the rate constant at two different temperatures. And we can look at an equation that will handle that. There are two ways to do it. Your book does it this way. You get the same answer no matter which way you do it. So your book has a natural log of the rate constant at temperature 2 divided by the rate constant at temperature 1 equals negative EA over R times 1 over temperature 2 minus 1 over temperature 1. Different books will have it this way. Natural log of K1 over K2 equals EA over R times T1 minus T2 over T1 times T2. Believe it or not, this expression here, T1 minus T2 divided by T1 times T2, gives you the exact same answer as 1 over T2 minus 1 over T1. Okay, the natural log of K1 over K2 over here is the same as the natural log of K2 over K1 if you make the other side negative. So this negative sign here that's not over here takes care of the K2 and the K1 flipping, and this term is the same as that term. When I worked out this example, I worked it out using this formula, but I have since worked it out using this formula. You get the same answer either way. But here's an example. The rate constant for a first order reaction is 3.46 times 10 to the minus 2 per second at 298 Kelvin. What's the rate constant at 350 Kelvin if the activation energy is 50.2 kilojoules per mole? So when you work this out, first thing we can notice is we've increased the temperature. And since we remember, well, the reaction rate should double for every 10 degrees we increase the temperature. Every 10 degrees Celsius we increase temperature. We'd expect that the rate constant will be larger, indicating a faster reaction. But you just throw the numbers in there, and if you want to, you can find out, you can do it yourself. This math here, the T1 minus T2 part, gives you the same answer as here. You do the math, make sure you account for a number of things. The two things you have to watch out for here is our R is 8.314 joules per Kelvin mole, whereas our activation energies are always given in kilojoules. So you need to convert this 50.2 kilojoules into joules. And the way you do that is very simple. Take the decimal place and move it 3 places over. So this 50.2 kilojoules is 50.2 times 10 to the third joules. Now that's not scientific notation, but if you put it in your calculator, you'll get the right answer. And you work it out, make sure you can get rid of the logs with E, and you get K2 equals 0.702 per second. A larger rate constant means the reaction is faster. Alright, we're going to keep this video a little short because I want to try to keep the next section, reaction mechanisms, all in there together.